In this lesson, I want to touch upon a very important concept that will continue to build on throughout the semester. And so first I'm going to start with the electron configuration of carbon. You may remember figuring out the electron configuration in general chemistry for many different atoms. That's not going to be high yield in organic chemistry, but it's important for us to understand hybridization as a model, right? So electron configuration of carbon, and then it's in its ground state in this case. Okay, and so we look, these two comprise the 1s, and we have 2 electrons there, and so we have 2 in the 2s is filled, and then 2 in 2p. So we'll get 1s2, 2s2, and 2p2. That's the electron configuration for carbon. And so when we look at valence bond theory, we have 2s, 2p, there's 1s orbital, there are 3p orbitals. I'm going to exclude the 1s, it's implied, right? And so we're only looking at valence electrons, and so we have 4 total in the valence shell, so 2 in the s, and then 2 in the p. Remember, we space these out until we can't space them out anymore, then we double up on electrons, right? And so this is the model that we have as of now. But we know something about carbon that's found out through techniques like X-ray diffraction, that these 4 bonds are essentially equal in energy. However, this model does not suggest that. Why? Because it's suggesting that the bonds that would form in the p orbitals, essentially, would be on a higher energy level than the bonds formed in the s orbital. And so this model is not an accurate representation of the way carbon likes to form those 4 bonds in CH4. Right? And so we'll need a new model to account for this. Now, before we jump into that new model, we'll need to understand a little bit about orbitals. So this is a terrible circle. Let's see if I can do better. So here is the nucleus, and this is the s orbital. What is an orbital exactly? An orbital is essentially nothing more or nothing less than a probability cloud. So it's the most probable location of finding an electron. Okay? And so for the p orbital, there's a node in the middle. A node is not a nucleus. It's not a nucleus, but a node is essentially the absence of electron density in that space. There's absolutely 0 probability of finding an electron there. So absence right? And so that's what a node is. And so now we have the s orbital defined and the p orbital defined. Let's go ahead and go back to this model. And so we have 1 s orbital, and we have 3 p orbitals. 1, 2, 3. And so let me draw them out. I'm going to keep it in black. You'll see why in a second. There's that. These should be equal sized dumbbells, even if my depiction is not as great as it should be. But let's take a look at these electrons. So this electron is essentially going to be anywhere inside this shaded red area. So the probability of finding an electron is anywhere in this shape. The second electron is also in a p orbital. And again, it's anywhere you're going to find it anywhere floating around, whizzing around in that shaded dumbbell area space, right? And so there's an empty p orbital in this case. So we have an empty p orbital, and then we have our s orbital with these electrons. They could be floating around essentially anywhere in this sphere around that nucleus, right? And so, like I said earlier, there's a problem with this model. It shows that there are some bonds that form that are going to have higher, oops, wrong pen, they're going to have higher energy than others when we know that carbon has four bonds that are all equal in energy in CH4. And so we need a new model to account for this discrepancy. So let me redraw. We have 2s and 2p, the 1s orbital and 3p orbitals. What we're going to do, actually, I'll draw these out. Oops, don't like that. Getting worse. There we go. And then we have our s orbital there, right? So these orbitals, what we're going to do is we're going to take them and we're going to mix them. Imagine mixing something in a blender. And so this is the process of hybridization. Right? And so now we get 4 equal energy sp3 orbitals. We've mixed these orbitals together, the s and the p in a blender, and then we get 4 sp3 orbitals coming out the other side. And so now these sp orbitals look like a mix of the spherical orbital, so these kind of balloon out a little bit more, right? And then the p orbital. They still have a slightly dumbbell-esque, for lack of a better word, dumbbell-esque shape. So these are 4 equal sp3 orbitals. And so now we can essentially account for carbon having 4 equal energy bonds. And so this better fits our model. So let's take a look at recapping this. These will also have nodes here, areas where there's an absence of density. Now, there are other ways we can also mix those orbitals. So this way, let's go and say this essentially was an example representing CH4. Actually, let's draw it out. CH4. How else might we be able to mix those orbitals? Let's take another example. This time, we'll do C2H4. So same model at first. We have our 2S and 2P. Right, now what we're going to do is we're going to essentially, I'll go ahead and actually, since my artwork is phenomenal, I'll go ahead and copy this over. Okay, so here are my orbitals, and then again, we're going to mix them. Hybridize them. And what are we going to get now? Essentially, we're going to have one unhybridized p orbital and three newly hybridized. Let me actually correct this slightly because I need to take into account energy relative to those orbitals. They're going to be somewhere in between these two in energy. So if I were to draw a line over somewhere in between, I'll have my three orbitals, and then the p will stay exactly at the same energy level. Guys, see that? It's a subtle thing to understand. But when you hybridize, they go down in energy relative. Ooh, I'm not going to be able to reach that. But relative to what was before in terms of between the 2p and 2s, because they are now a mix of 2p and 2s. And so we get three hybridized sp2 orbitals and one unhybridized p orbital. So now you have same shape as the sp3, just a bit smaller, and then you have your unhybridized p orbital. And in fact, to make sure I'm staying true to the right size, I'll just copy that over and paste it over here. Right, so we have three hybridized p orbitals, three hybridized sp2 orbitals, and then we have a unhybridized p orbital. All right, so that's another way we can mix, we can hybridize. There is a third and final way we can hybridize. These orbitals, and so we'll do C2H2. And so again, we take our model, our pre-existing model that does not apply for that. Go ahead and take all of this and paste it down here. And now we'll go ahead and mix these. So we're going to hybridize these orbitals, and now we're going to get two sp hybridized orbitals, and then two unhybridized p orbitals. And so I'll copy these over here because they were unhybridized, meaning they were not hybridized, so they stay unhybridized. And then now we have even smaller there we go, sp hybridized orbitals. All right, so there are three ways to mix them, and essentially we get three different types of hybridized orbitals. We get sp3 hybridized orbitals, four of them, all of them equal. So let me write that down as I did in the other cases. We get four hybridized sp3 orbitals, and in this case we have three hybridized sp2 orbitals and one unhybridized p orbital. And then lastly, we have, do it in red, two hybridized sp orbitals and two unhybridized p orbitals. These hybridized models essentially are more accurate indicators of the bonds that we form in these different examples. So I'm going to zoom out so we can get a better overview. And so those are the three ways we can hybridize our orbitals. And so hybridization is nothing more than the mixing of orbitals to form hybridized orbitals and to account for different types of bonds to carbon.